Okay, this lesson is titled Linear Functions and Their Slope. A linear function is represented by a straight line when it's graphed, and represented by an equation where the variables have no whole number exponent higher than 1. There are three forms of the linear equations that we're going to be looking at today. The standard form is ax plus by plus c equals 0. Again, notice that the variables x and y have no exponent higher than 1. But the variables a, b, and c, which will be constants when we actually have a real equation, are going to be all whole numbers, which makes the standard form a very pretty equation with all nice whole numbers, no fractions, and very nice to look at. The slope-intercept form is y equals mx plus b. Now we have different constants b and m here, which means something. We'll talk about that. But notice that our variables x and y are our variables, and they don't have any exponents higher than 1. And in slope-intercept form, the m represents slope, and the b represents the y-intercept. On the last form, we have point-slope form, which looks like y minus y1 equals m times the quantity x minus x1. Again, my variables x and y don't have any exponent higher than 1, but we do have a lot of other constants that we have here, so we'll just find out what those constant means. The m still means slope. And every time in this section we talk about m, that's going to be talking about slope, whether it's in slope-intercept form or point-slope form. Notice that both of these talk about having a slope in the form. The x1, y1, when put together as an ordered pair, gives me a point on the line. So these are the three forms of the linear equation. Today in our lesson we'll be graphing from these forms as well as writing equations from these forms. Next, we'd like to know, when is it useful to use each of these forms? Well, standard form, again, I said was kind of like our pretty form. And I said that was our pretty form because we have no fractions. No fractions because in the definition a, b, and c are whole numbers. Because it's a pretty form, it's not very useful for lots of things. Standard form is useful for finding intercepts, the x-intercept and the y-intercept. And I say it's useful because it's easy to do it in this form, and we'll show you that in a little bit. The slope-intercept form is very easy to graph from. It's also nice when you're trying to write equations given a slope and a y-intercept. If you had the slope and the y-intercept, all you'd have to do is plug in the values. Now, most often, the book does not give you problems that are just given the slope and the y-intercept. They make you do a little bit more work, but if that's what you had, it would be very easy to write the equation. And lastly, I want to mention that you want to answer all equations in this form. The point-slope form is very useful for writing equations, especially when you're given a point and a slope, or if you're given 2 points. Also, it's fairly simple to graph if you're given a point and a slope. So those are the times that are useful for each of the forms. And we'll refer back to each of these forms as we approach different problems. Next, I'd like to talk about the steepness of a line. Put 2 points on this xy plane here. We'll call them x1, y1, and x2, y2. And we'll explore a little bit about the line that's connecting them. Okay, this line looks like it's going up and to the right, but more specifically, I'd like to know how steep this line is. I'd like to create a triangle here. connecting the 2 points with a right angle. I want to know how far am I increasing my vertical distance versus how far am I increasing my horizontal distance. And then I'm going to take that ratio and I'm going to get a value that gives me the steepness of my line. So the first thing I'd like to do is find out how far am I increasing. And we'll do this in blue right here. When I'm traveling from the first point to the second point, how far am I changing vertically? Well, if I move these values, y1 and y2 off to the side, you can see that I'm increasing from y1 to y2. And that distance is merely the second term minus the first term, or y2 minus y1. On this green distance right here, if I take my horizontal distance x1 and x2, if I'm traveling from point to point, how far am I traveling horizontally? Well, I'm just traveling the distance from x1 to x2. To find the distance from x1 to x2, I take x2 minus x1. So when I'm traveling from my first red point to my second red point, I'm traveling up a blue distance of y2 minus y1. I'm also traveling right a green distance, x2 minus x1. Mathematically, the way we talk about steepness is we call it slope. And the slope formula is y2 minus y1, or the vertical distance that we've traveled, divided by x2 minus x1, or the horizontal distance we've traveled. Another way of thinking about this is rise over run. My rise is my blue distance that I'm increasing vertically. My run is my horizontal distance that I'm increasing horizontally. And one last way we can think about that is using these symbols. It looks like triangle y over triangle x, but what that really means, triangle y means the change in the y direction, or change in y. Triangle x, or delta x, means the change in x. So we now have a definition for slope. More specifically, m equals y2 minus y1 over x2 minus x1. There's a couple different types of slope I'd like to show to you today. We have lines that increase from left to right. We have lines that decrease from left to right. We have some lines staying constant from left to right, and we have some lines that aren't going left to right at all. They're just going up and down. And each of these have a different type of slope. My first line, increasing from left to right, tells us that we have a positive slope. If my line is decreasing from left to right, that tells me that I have a negative slope. When I'm staying constant from left to right, that tells me that I have a zero slope. This vertical line has an undefined slope. A positive slope is going up a positive direction and up a positive. So a positive over a positive, if you're thinking of your rise over the run, a positive divided by a positive is going to get me a positive, which is why we have a positive slope. On our negative slope line, my vertical direction, well, my vertical isn't increasing at all, it's decreasing, so it's a negative change. But my run is still increasing, so that's a positive change. To get my slope, I'm taking the rise over the run, a negative divided by a positive, and that gets me a negative, which is why we have a negative slope here. It even works for the zero slope. Remember, rise over run. Going from 2 points on my line, how far did I rise to get from the first red point to the second red point? Well, I didn't rise at all. How far did I run? Well, I ran a positive distance, but 0 divided by anything is still 0. For the vertical line, if I put 2 points on there, and I'm again thinking rise over run for my slope, the rise, well, I'm increasing a positive distance, but how far am I running horizontally, left to right? Well, I'm not going left to right at all. One positive number divided by 0 is undefined. Therefore, I have an undefined slope. In the next couple examples, I'd like you to find the slope for the following pairs of points. Then I want you to plot those points and draw the linear function containing those 2 points. So my first points are 6, -4 and -4, 2. I know I have a slope formula that says y2 minus y1 over x2 minus x1, or rise over run. But my question to you is, who's x1 and who's y1? We know that x is the first coordinate, so we'll call the first coordinate x and the second coordinate y. And this side is my first point, so I'll call him x1, y1. And the other one I'm going to call x2, y2. I'm just labeling the first x and the first y, the second x and the second y. So that when I come back in and I use the slope formula, when I read y2, instead of y2, I'm going to replace it with 2. Minus, because there's a minus in the formula, y1, and my y1 is -4. x2 is -4 minus x1, and I replace that with 6. 2 minus the -4 is really add 4, or 6. -4 minus 6 is -10. 6 over -10 reduces to -3/5. So my slope is -3/5 for the line passing through the 2 given points. Next, I was asked to plot the points and draw the linear function. 6, -4 and -4, 2. And I can connect the line between them. And I'd like to point out that slope is rise over run. If my rise is -3, that means I'm going down 3. If my run is 5, then I'm going right 5. Notice that's a point on my line. Let's do it again. If I rise -3, which means go down -3, and I run 5, I end up right where my point is. So is this a correct slope? Yes, it is. I can see that by the graph. Again, I'm going to label my x1, y1 and x2, y2. My slope is y2 minus y1 over x2 minus x1, or 4 minus 4 over 2 minus a -3. 4 minus 4 is 0. 2 minus a -3 is 5. And 0 divided by 5 is 0. So I believe my slope is 0. Next, it asks me to plot the points. -3, 4, and 2, 4. I connect my line. Remember, we said slope was rise over run. This slope is 0. I'm rising 0, and I'm running in the unreduced form 5. So if I rise 0 and run 5, I am getting the points on my line. Last, I'm going to label my x1, y1. y2 is equal to 2. Minus, because there's a minus in the formula, y1 is equal to 5. x2 is equal to 1 minus x1 is equal to 1. 2 minus 5 is a -3. 1 minus 1 is 0. -3 divided by 0 is an undefined number. We cannot ever divide by 0, so I have an undefined slope. Next, it asks me to plot the points. 1, 5, and 1, 2. And when I connect these points with a line, I'm getting a vertical line. Remember, my slope was rise over run. My rise is -3, I'm going down 3, and I'm going left and right 0, and I'm finding myself at the other point. So this is correct, and this truly has an undefined slope. Notice on our first example we had a negative slope, our second example we had a 0 slope, and the third we had an undefined slope. Well, the 0 slope and the undefined slope are special cases. So we have an acronym called Hoy Vuxt to help us remember our special cases. And our special cases are horizontal lines and vertical lines. The Hoy stands for horizontal lines have 0 slopes. I know that's an O, but it's also going to be a 0 for our purposes today. And their equation looks like y equals some number. For example, y equals 3. Notice it's y equals some number. I know that that is going to be a horizontal line, and I know it's going to have a 0 slope. Similarly, Vuxt stands for vertical lines have undefined slopes. And their equation looks like x equals some number. For example, x equals 1. I know that it's going to be a vertical line, and I know it's going to have an undefined slope. Here's your example of the vertical, and then similarly here we have an example of the horizontal line. Next, we're trying to graph using a point and a slope. In order to graph using a point and a slope, I first want you to graph the point. Then I want you to use your slope to find another point. And I want you to think rise is the numerator and the denominator is your run. So once you find your slope, the numerator is going to be your rise, the denominator is going to be your run. If your slope is a whole number, then put it over 1 to make it into a fraction so that you have a numerator and you have a denominator. Next, I want you to connect your points with a straight line using arrows at the ends, meaning that this does go on forever. My first example tells me to graph using a slope of 3/5 and through the point 1, -2. My first step says graph the point. So I go to 1, -2 and I plot that point. To get the next point, I have to use my slope. My slope is 3/5. My 3 is going to be my rise and my 5 is going to be my run. From this point, I would like you to rise 1, 2, 3. Now don't put your pencil down yet because we still need to run 1, 2, 3, 4, 5. Your rise is how far you go up or down. Your run is how far you go left or right. Once I have at least 2 points, I can connect using a straight line and put arrows at the ends of your graph. Next, I'd like to graph a line with a slope of 0 through the point 1, -2. I plot my point 1, -2, and this time I have a slope of 0. Well, there's a couple different ways of thinking about this. You could put your 0 over 1, and that tells me that my 0 is my rise, and my 1 is my run. If I go up and down nothing, or 0, yet I run 1, I can get another point. You're welcome to repeat this process. If I go up and down nothing and run 1, I can keep going and get a lot of points. Connect them with a straight line using your arrows. Another way of thinking about this is using your Hoy Vuxt. I know that I have a 0 slope. Because I have a 0 slope, that tells me that I have a horizontal line. So all I really had to do was plot my point and then draw a horizontal line through it. On the third example, I have an undefined slope through the point 1, -2. Again, I plot 1, -2 first, and then I use my slope to find another point. If we're looking for the special cases, we know that an undefined slope is either a vertical or a horizontal line. Well, my Hoy Vuxt says that my U, undefined, slope has a vertical line. So I could just take my 1 point and know that it has a vertical line through it, and then I am done. The other way of thinking about an undefined slope, if I have an undefined slope, that means I must have a 0 on the bottom. What number can I have on top? I don't really care what number, we'll pick 1. If 1 is my rise and 0 is my run, I could go up 1 and left and right nothing, put another point. Up 1, left and right, nothing, put another point, and so on and so forth. Notice I'm still getting a vertical line. So you can either think of your undefined slope as 1 over 0, using your rise or your run, or you could use your Hoy Vux and just know that any line with an undefined slope is going to be a vertical line.